Welcome once again, all the residents of Shobha Forest View and Ujjain Engineering College students. So, welcome everybody. Yesterday, we did just an introduction to neural networks, which was nothing but a just kind of warm up exercise for us. So, just to understand what you can expect going forward. So today we'll go a little deeper and solve some useful neural network problems. So some useful means useful in the simplest form. A neural network is called artificial neural network, which is ANN. So ANN is a type of neural network which you can apply in both in logistic regression category, and you can apply both in logistic regression category and in classification problem also you can apply it, and you can apply it in regression problems also. So that's what ANN can do, both classification and regression. Okay. So now it is okay. So I repeat yesterday's some stuff which we did yesterday. So in a neural network, we have an input layer. You see the left hand side diagram. We have an input layer. We have two hidden layers here. So hidden layer 1, hidden layer 2, and one output layer. So we can have multiple hidden layers. So here I have shown 2, but in effect we can have say 10 hidden layers, even up to 100, few hundred hidden layers also we may have. And here we have shown only three neurons in only 3 neurons each in the hidden layer, but we can have say up to 2000 neurons also in a single layer. So up to that extent we can go. And now why there are 2 neurons in the output class? Output layer, why there are 2 neurons? That is because we have only 2 classes in the our target variable. Only 2 classes are there. This is a classification type of problem. So there are only 2 classes. So one neuron will tell probability of occurrence of one class 1, and second neuron will tell probability of occurrence of class 2. So there are two neurons. Then now let us go a little ahead. So weights between input layer and the first hidden layer are called W1. Set of weights, W1 is a vector matrix. So between the input layer and first hidden layer, what we have is called W1. Between first hidden layer to second hidden layer is what we call W2. And what between second hidden layer to output layer, what is there in between is called W3. So these are all vectors. So don't worry, or don't assume that it is very difficult. We'll see one by one what kind of vector is it. Okay. So let us first see a simple neural network input layer with 2 inputs, x1 and x2. 2 inputs are there. Then there is one hidden layer with 3 neurons. 3 neurons. 1, 2, 3. 3 neurons are there. So you see there the number one input node, which is the first neuron, is connected to all the 3 neurons of the hidden layer. You can see the connections. And the second neuron also is connected to each and every neuron of the hidden layer, all the 3 neurons. So all neurons are connected to each other, and all feed is going forward. Nothing is backward. Okay. So feed is going forward, and all neurons are connected to each other. So we call it as densely connected. We call it densely connected dense layers. We call it dense layers or densely connected layers because all the neurons are connected to each other. Now, let us understand a little bit about the notation. Okay, so first consider the first input 1. First input neuron 1. So weight between first neuron and the first hidden layer neuron is W11. Weight between first neuron and second hidden layer neuron is W12. And weights between first neuron and third neuron of hidden layer is W13. Okay, then similarly second neuron, if you take second neuron connected to the first neuron of hidden layer, that is W21. Because second neuron of hidden input layer we are talking about. Then second input neuron from second input layer neuron to second hidden layer neuron. So it is W22. And lastly, next connection we have is second neuron of input layer connected to third neuron of the hidden layer, that is W23. So this gives a little idea about notations. Notations are very important. So how we play the notations. So this is how we do the notation of the weight. And this matrix, these weights can be written in the form of matrix, which are given in the right hand side of the figure. So there is a matrix which you can see W11, W212, W13, W21, W22, and W23. They are all given in the subscript. And whatever is the superscript 111, each weight is having a superscript of 1. Superscript of 1 means it is first, they are first hidden layer nodes. They are first hidden layer neurons. Okay. They are nothing but first hidden layer neurons. So W1 superscript and W11, 12, 13, 221, 22, 23. Like that we are showing. So superscript is always showing the number of layer. Input layer we don't count. So first layer means it will be our first hidden layer. So first, so like that. Two inputs are there. So inputs are again shown as a vector x1, x2. And output from each neuron is denoted as h1. h1, h2, h3 collectively which shown in the right hand side, that is denoted by capital H. So capital H is nothing but a vector of h1, h2, h3, 3 elements. Capital W is nothing but a vector of 2 rows by 3 column matrix. And input is also a vector x1, x2, which is a matrix of x, only 2 units, x1 and x2. So how we get the output? See vector notations. So x is a, see it on the top of, on the very top of the right hand side figure, it is written capital X dot W is equal to H. In a simple notation we have shown the output. So if I multiply input vector X to weight matrix W, I get the output vector H as a vector. Very simple vector algebra. And this is X dot W is nothing but a dot product. Don't worry. Don't get even at this stage also don't worry. We'll simplify it further as going forward. It will get further simplified when numerics will come. Okay. So now again I repeat the same perceptron of yesterday's class. So input is x vector, weight is W is weight, bias is B, Y is the output. So Y is nothing but output of that neuron. So Y vector is nothing but output of that neuron is equal to sigma of weight and input. We see W1 x1 W2 x2 yesterday. So we first do sigma of weight and input plus we add the bias term. This is what is the equation. Okay, it's very simple equation. Yesterday we have already appreciated and worked with this equation a bit. Okay, so now I will tell you like which are the parameters and hyperparameters of the neural network. So can anybody attempt what is the difference between parameter and hyperparameter of a machine learning model? Anybody wants to take a shot? What is the difference between the parameters and hyperparameters of a machine learning model?
A parameter is go ahead.
Yeah, please tell me. No issues.
Go ahead.
Anyone go
No,
ahead.
it's
Yeah,
okay.
no issues.
Okay,
Yeah.
a parameter is something that is there as part of the training data, whereas a hyperparameter is something that is external to the data, like in our regularization function lambda, that is a hyperparameter.
Okay. You are telling right, madam, but I don't think you are defining it right. Parameters are regular elements of the machine learning model, like beta 0, beta 1, beta 2 of linear regression, which we get by training. So they are normal elements of machine learning model. Like in case of linear regression, they are beta 0, beta 1, beta 2 up to beta n. So these are the coefficients. They are nothing but the coefficients of x. coefficients of X, which we get by training. So normal thing. And hyperparameter is something which control the model up to a large extent. Just by tweaking little bit, if we tweak hyperparameter a bit, like you said, lambda, if we tweak, our model changes a lot. Okay, so hyperparameter is not something which we get by training. Hyperparameter is something which we supply externally, as you rightly said. Hyperparameter we externally supply, and by giving the right value of hyperparameter, we want to get an optimum model. So hyperparameter, if I compare, it is nothing but, say, it is the handle and accelerator of the car. Handle and steering wheel and accelerator of the car, hyperparameter. Steering wheel and accelerator, I would term that as hyperparameter, because they control how my car behaves, whether it goes left or right, how fast this goes. Okay. Then car tire, car body, car engine, transmission system, all these things can be called as, all other parts of the car can be called as parameters. Because car is a model, okay? Car is a model. So its tires, its transmission system, engine, body, everything is a model. So how they are controlled? They are controlled with the help of a steering wheel and an accelerator, right? So they are hyperparameter. They are hyperparameter of that model. So similarly, for every model in the machine, every machine learning model, we have certain parameters of the model which we get during the training. And hyperparameters are hyperparameter is something which is external to the model, which we supply to the model to get the optimum number of model. Okay. So how it is? The car, my speed limit is on the road, Indian roads is maximum speed limit is 80 km/h, right? So how I do that? So optimal, if I had to run with full fuel efficiency, I should drive my car between 40 to 60. That's when I get the optimal fuel efficiency out of my car, right? So how I do that? I control that with the help of steering wheel and accelerator, right? So they are my steering wheel and accelerator are nothing but my hyperparameter, which control my model. My model is nothing but other parts of the car. So similarly, we can apply same concept to the any machine learning model. So now here in neural networks, whatever weights we see here, all weights and bias here. Weights and bias are nothing but the parameter. Weights W and B are nothing but the parameters of the model. W and B are nothing but the parameters of the model, which we get by training the model with the help of input data. Whatever historical data we provide to the model, with itself, model is getting trained. Model is getting trained means we determine appropriate values of weights and biases. So weights and biases are nothing but parameters of our machine learning program, a machine learning model. Weights and bias is nothing but the parameters. X is the input. Of course, input is input, which is nothing but our historical data, image data or something. Y is the ground truth. Ground truth means we already know that which class is positive and which class is negative, right? We already know yes or no in our data. And with that data, we train our machine learning model. So we already know the ground truth. So that is called target variable. So target variable is known at the time of training. So that target variable we denote as Y. Pre is the probability vector of predicted output. Means whatever probability we get, these two, I told two probabilities are there, right? P1, P2. In this output layer, there are two probabilities. Probability of class 1 as P1 and probability of class 2 as P2. So this P1, P2, this value is nothing but denoted by small p. So this small p is the probability vector. So P1 and P2 collectively, when we represent in a matrix, P1 and P2 are scalar numbers, right? Between 0 and 1. Both are between 0 and 1 because that is probability. But when we denote both P1 and P2 together in a matrix, simple matrix, that is nothing but a vector. It becomes a vector. So that is nothing but that is denoted by P. H is the output of all the hidden layers. So here you see H1, H2, H3 is nothing but it is the output of all the hidden layers. And when collectively we represent H1, H2, H3 in a matrix form, then it becomes a vector, which is denoted by capital H. Okay. Then superscripts stand for a layer number. I told you here. W1 superscript is stand for the first hidden layer. If it were layer 2 means it will become W2. Then subscripts stand for the index of the individual neuron. So first the W11 means first neuron connected to the first neuron of next layer. W12 means first neuron of left layer connected to the second neuron of the second layer, input second layer, next layer. W13 means we know that, right? So this is how our notations are distributed. And only thing which I want you to understand here is that our model parameters are weights and biases are our model parameters. Rest H1, H2, everything we can calculate with the help of equations. Okay. So here model parameters is when we train the model, that means we are determining the correct value of weights and biases. So there are how many weights are there between, see here left hand side there I have shown a neural network, small neural network with 2 input nodes and 3 hidden layer nodes. So can anyone tell me how many weights will be there in between the input layer and hidden layer? How many weights will be there?
6.
6 weights, right? 3 into 2, right? How many biases will be there?
Usually I think one is added.
No, one bias vector will be added. But
how
much will the value of the bias?
3.
3, yeah. One for and will there be any bias for the input nodes 1 and 2?
No.
Yeah, so bias will be there only for the hidden layer. Each and output vector also there will not be any bias. Okay. So all hidden layer, every neuron we add one bias. So one bias for P1, B1 for B1, B2, B3, 3 bias we add. And when we represent B1, B2, B3 together in a matrix, it becomes a vector. It is denoted by B. So weights and biases between all the layers is what is our job as a machine learning engineer to calculate their right value to make up our complete neural network. That is what our job as a machine learning engineer. As a machine learning engineer, our job is to find the correct value of weights and biases. So these are nothing but model hyperparameters. Sorry, model parameter, weights and biases. Now, which are hyperparameter? You will ask, which are hyperparameters? Number one hyperparameter is in neural network is learning rate, which I have not explained to you. We'll see it going forward. Don't worry about it right now. Now, going forward, we'll see how much is the learning rate of neural network. That we'll see going forward. Don't worry for right now. Okay. Then number of iterations. How many number of complete training cycles we give to this neural network? In every training cycle, from a new input layer to from every when we give input here, when we give input to the input layer, that the data will pass, all the input data will get multiplied to the appropriate weights and pass through hidden layer 1, hidden layer 2, and ultimately output will get output as probabilities P1, P2, right? So from input layer to output layer, one cycle is called forward pass. It is called forward pass because it's going forward. And then if our error calculations, like when we get outputs, we compare it with the ground truth. These are the values predicted by the model. And this is what are the really I know the real value are the probabilities are P1 is say 0.8 and P2 is 0.09. So what will be the model output? I'm asking you a simple question. P1 is 0.8 and P2 is 0.09. So what you will consider as output of the model? It is class 1 prediction or class 2 prediction? Class 1 probability I am telling is 0.8 and class 2 probability shown by model is 0.09. So what you will consider as the output of our prediction of the model?
Class 1.
Class 1, right? Why class 1?
Because the probability is closer to 1 there.
Probability is closer to 1, right? You got it very right. Now, I will compare it with ground truth which I have. I will compare with what, because in training data I also have the true values. Okay. So my model output is showing class 1, and the real data, real answer which I have is also class 1. Then it is okay. My model prediction is correct. But if model is predicting class 1 and the real data, real answer of what I have for this input is class 2, that means model prediction is wrong. Model is predicting class 1 and the real answer is class 2. So in that case, what I will do? I'll take the difference of this, difference of that, and I'll go one pass back. So I'll go back. Back means output layer 2, hidden layer 2, hidden layer 1, and input layer 1. Back pass I will do. Why I will do back pass? In that back pass, I will appropriately update weights and biases. Every forward pass is nothing but the calculation. Forward pass is a calculation. What calculation? Output H is equal to X into W. You see the here equation, capital X dot capital W is equal to H. So this is what is the forward bias. Forward pass. In forward pass, weights are not getting updated. In the backward pass, when our model prediction is wrong, that time we'll take the difference of predicted minus actual, same as linear regression. Like predicted value minus actual minus predicted value, we take and do the square, least square method, right? The same thing we do, least square, take a derivative of it and propagate backward. Error we propagate backward, and we update our weights and biases in the backward pass. So in training cycle of neural network is 2 steps. One is forward pass, one is backward pass. If right now it is not understood, you just remember one is forward pass. So forward pass is nothing but calculation, this calculation. Input into weights is equal to output. Like that we do for every layer. This is for forward pass. Backward pass is predicted value, actual value minus predicted value. We take the square, we do the square, we do actual minus predicted value, and then that error we propagate through backward. We take a derivative, a partial derivative with respect to every weight and bias, and we propagate it backwards to update our weights and biases. So forward pass, one plus one backward part is our complete training cycle of the neural network. It will be clear going forward. Don't worry. You just listen for now. Don't get intimidated or overwhelmed or worried by these big terms. It will get further clear going forward. Okay. So one forward pass per one backward pass together forms one training cycle. In backward pass is more important because that's where our weights and biases get updated. Okay. So that is one cycle is called epoch. So EPOH, it is called EPOH. Today I have not connected the iPad, so I cannot draw and write. So spelling is EPOH, epoch. So it is called one epoch. Epoch means a complete iteration, one forward pass and one backward pass. So one iteration is called EPOCH, epoch. One epoch it is called. One epoch, one iteration is called one epoch. So one EPO is what the number of EPO also is a hyperparameter. Why is it a hyperparameter? Because in each backward pass we are updating weights and biases. If we are taking more iterations, more number of times my weights and biases will get updated. So more number of times my value of weights and biases will get upgraded. So that if I keep number of iterations less, what may happen? I may get a suboptimal model because my weights and biases are not still completely calculated. Suppose I need 100 iterations to reach one complete. I need 100 iterations of total 100 iteration of neural network to get a accuracy of say 80%, prediction accuracy of 80%. I need 100 iterations. 100 times I need to update my weights and biases during the backward pass, right? But I have done only 25. What will happen? Can anybody guess? I need 100 iterations totally to completely update my weights and bias, ideally. But I do only 25 iterations and stop. What will be the result of that?
The accuracy will be pretty low.
Pretty low, right? Why it will be low?
because I haven't really adjusted the weights and biases to reach that high level of accuracy. That many.
Right, exactly. So number of iterations also is a hyperparameter, and that we don't know before training. Okay, it depends on the data set. Number of iterations we may need, it depends on the data set. So that is also a hyperparameter. So that we have to use sometime. We have to determine it also by trial and error. Okay, you have to determine it by trial and error. So we first try with 20, then we try with 25, and we plot a graph. If we see whether our accuracy level or error level is constant, that means we understand that convergence is reached. We plot a graph. I'll show you that graph. Which one is that graph? I'll show you this graph. You see this graph. This is the graph I will show you. This is the graph we plot. This is the graph we plot. Okay. So this is nothing but performance. Performance versus amount of data. So for a data level, like a similar graph actually we plot, not exactly this graph. So when this curve becomes parallel to x-axis, means our performance is no longer changes. We go on increasing we take iterations on the x-axis and performance on y-axis. Number of iterations on x-axis and performance on y-axis. So now we are keep on increasing iteration to 100, 10, 200, 300, 400. But when our performance curve becomes parallel to x-axis, that means we have reached the convergence. Whatever number of iteration now you do, your accuracy or performance is not going to improve. That is the stage where we have to stop doing iterations. And why we have to stop? Because every iteration is money. Why it is money? Because it is computational time. So very costly computational resources you have to spend because neural network training is anytime very costly actually. So that is why I am insisting you guys to take each one of you to go for Google Colab Pro, because in your normal machines, 8 GB machine with Wi-Fi and all that, it may take 10 hours, 20 hours to even to train a single neural network. So that's where you need some kind of cloud assistance. So it is very costly to train a neural network model. So number of iteration is another hyperparameter. Then another hyperparameter is number of hidden layers and the number of neurons in each hidden layers. How it is, you see. Here is the neural network. So here I have put 2 hidden layers, 1 and 2 hidden layers. I can go and put 5, I can go and put 10, I can go and put 20. So that is another hyperparameter. So that the more is a hidden layer I put, the complexity of my neural network increases. Now here I have put 3 neurons each in hidden layer, only 3 neurons in each. I can put 30, I can put 20, I can put 300, I can put 1000 neurons in each layer. I can put 1000 in first layer and 500 in second layer. So that also is a hyperparameter, because number of neurons and number of layer determine how complex our neural network is going to be. If neural network is, if you are building a very complex and heavy neural network, that means it can represent it has very high number of trainable parameters. All the weights and biases will be very high. Number of weights and biases very high. If I take 10 hidden layers like this, and every layer if I take 1000 neurons, there will be more than 1 lakh or something total weights and bias. If I include, there will be more than 1 lakh, more than 100,000. So everything I had to determine during my training only. So what is the meaning of more weights and bias? If weights and bias are more, means I have more model parameters. I have more model parameters. That means I have represent more complex relationship between target variable and independent variable. If my relationship between target variable and independent is linear, I need only one hidden layer. I need only one hidden layer. That's all. If my relationship is a little complex, say square, I may need 2 or 3 hidden layers maximum. If my relationship between the independent variable y, dependent variable y, and independent variable is cuboid, or x to the power 3 or x to the power 4, then I have to add a couple of more hidden layers. Like the relationship between y and x become more and more complex. So my neural networks also becomes more and more complex. I go on adding more and more layers, and I go on adding more and more neurons in the each hidden layer. So that is a big hyperparameter. Okay, so this is nothing but called total neural network architecture. So determining right number of layers is one hyperparameter. That is one hyperparameter. Another hyperparameter related to that is in each hyperparameter, in each hidden layer, how many neurons I should have. Hidden layer 1, I can have 20 neurons. Hidden layer I can have 20. Then hidden layer 3, I can have 10. Hidden layer, then I can reduce it actually, or I can go on increasing it. Hidden layer 1, 24. Then I go for next layer. I put 48. Then I put 48 into 2. Then I put one more hidden layer. Put into 48 into 2 into 2. Like that, I can go on increasing. So that is also a big hyperparameter which we determine with the help of. With the help of training only, we determine that. So that is another hyperparameter which is there. And there is something called activation function. So each neuron, when there is the output, we will going forward, we'll see that each neuron will have its own activation function. Activation function is something which we discussed in the last class also. We discussed only one activation function, step function. So whatever we did, our output was only step function. So that was the activation function. And after the class, I explained a couple of more activation functions, like one is sigmoid, one is softmax, one is ReLU kind of, then one is leaky ReLU. So different kind of activation functions you can put, and each neuron of each hidden layer has the activation function. Okay, so that also changes the behavior of our neural network. So you see, neural network is a very complex system. If you see, if I give you a neural network with 10 hidden layers, each hidden layer is having say 2000 neurons. So how many number of trainable parameters will be? We'll determine it. I'll tell you how to calculate total number of trainable parameters going forward. Okay. So compared to linear regression, logistic regression, or any other machine learning model, any sensible neural network will have very high number of trainable parameters. Trainable parameters mean model parameters. Very high number of model parameters are there, and each one we have to determine in the backward feed only is the process where we determine each one of weight and each one of the bias is calculated during the backward pass. So that's why the training time of any neural network, artificial neural network is very high compared to any other machine learning model like linear regression, logistic regression, or random forest or XGBoost. Compared to these traditional machine learning model, training time of neural network is very high and it requires very large amount of computational resources. So you got this idea about model parameters and hyperparameters. Okay. Then hyperparameter value is what we control. We will have one separate lecture on hyperparameter tuning of neural networks. And in the next course, we will see how to optimize hyperparameters. So there is a separate class I have kept how to do hyperparameter tuning of neural networks. We'll take a separate class of that. So first, I want to show that when we say that here, we say that Wx dot x, capital X dot product, and capital W is equal to H. What happens there? You see here, it is here. So the weight matrix is W into X1. So X1, X2, X3 is nothing but the input. We multiply it with weight. So say weights are W11, 12, W1, this is weight matrix. So dot product of input matrix and weight matrix is given here. You see the right hand side. Plus we add bias. It becomes one single matrix on the right hand side. W11 X1, W12 X2, W13 X3 plus bias 1. And superscript will be 1. So this is for only first, one first hidden layer, these calculations are there. Only for first hidden layer. Then once we have this Wx1 plus B, we apply the activation function on the top of that. You see the bottom, you come to the bottom of the right, then it is the sigma in the bracket capital W. Then we have input plus bias. So like that we apply activation function. So when we apply activation function, it applies to the each row of the matrix. You see, each row of the matrix is applied that particular activation function. So it looks complex, but if you remember your matrix and determinant algebra, linear algebra from your college days or your 12th class, so it is very elementary matrix algebra or and this none of these things we have to do. All computer will do. I have just shown it here so that you understand what is this is all during the forward pass. So what all happens during the forward pass is shown here. There is nothing to worry, because if you want to understand, you understand. Otherwise, if you choose to ignore, the heavens are not going to fall. Okay, that's how it is. Then I want to tell you the feed forward pseudocode for m data points. So for m data points means suppose you have m number of rows in your data set. Your first loop runs from first data point to your m data point, first row to m row. Then you first initialize your first output. First output means this is h, right? This is h1, h2, h3. So first h you initialize with the help of input only. Then for every layer, from 1 to all the layers in the network, you calculate the HL. You calculate the output. Output is calculated using this equation: sigma Wx plus B. Sigma Wx plus B plus bias. And then in the last layer, what you do? You apply a softmax function or a sigmoid function to the final output. Final output is where? Final output will be after hidden layer 2. So after hidden layer 2, you will apply one more activation function in the output layer, which is, if it is a classification, 2-class classification means you will apply softmax. Sorry, if 2-class classification means you will apply sigmoid, and if it is a multi-class, you will apply softmax. So these things will be going forward. These things will be clear. So don't think that this is too tough or something. I'm just telling you this is what is the feed forward equation. So if you want to solve with the help of NumPy, if you don't use TensorFlow, and if you want to write your own feed forward equation from scratch, just follow this pseudocode, and these same equations will, with the help of NumPy library, you can easily calculate. You can easily do your own feed forward from scratch. You need not use TensorFlow or anything, but we'll not do that. We'll use the TensorFlow, which will automatically do all of these things for us. So at this stage, I want to break it for 5 minutes.